Hi, we can wait for a few minutes and then start. In the meantime, if you guys have any questions, I can take them. Yeah. Okay, I guess we can start. Um, so let's recap some things that we saw last week. Okay. The first is the auto data type. So let's say we just use auto and try to initialize some variable x equals to 7. So the compiler at compilation time itself will determine the type of x. So accordingly, it will allocate memory. Okay. So um, like so to store 7, you can allocate integers, but generally it will try. So it decides that it's an integer type, but generally it will try to give it a data type which is the maximum system computer can store. Okay. So in my system, it is 64-bit. So it will store like a 64-bit integer. Then, yeah, like we see, let's say I have a map. Okay. I'm defining a standard map. It takes integer inputs, like as in it has to be templatized. So it's like a map. Map is, you can think of it like it has key value pairs, right? So the first is the uh, type of the key, and the second is the type of the value that it corresponds to. So map itself is not it's little it's a different data structure than your lists, or like we see standard arrays or standard vectors, which are lists, um, where each of the value is like there's a correspondence to these index. So let's say from 0, 1 to n minus 1, where n is the size of the list. So each value corresponds to a specific value. Okay. And that value could be integer, double, or whatever. But in maps, you have a key. So as in like that key could be integer or double or something. Then it corresponds to some other value. The value itself can be even vectors itself. Okay. Yeah. So here is just an integer. So to the example to take here is the map.begin, where the uh, begin function of map. Okay, so begin is a member of this class, actually map class. So what it returns is the iterator. So as we discussed last time, iterators are a little different than your something called pointers. So in lists, you have pointers where depending on how much you move by the index, the shift itself, so by 1 or 2 or whatever, the uh, pointer or the computer in general knows which address to look at, because it knows the data type of the list. So in case of standard vectors, or let's say doubles or something, it knows that doubles are of size, let's say, I mean, in general, they are 64-bit. So 64 bits of data I'll shift, okay, or 8 bytes, and I'll look at the next data. Okay, so the addresses themselves uh, can be passed, okay, in a list by using just pointers and shifts. Like if you know the starting point, starting address, which is what the pointer stores, you can get every other data by just shifting. Okay. No. Sorry. But in cases of, let's say, maps and such, like I discussed, we do not have any index as such. It's just let's say a standard map has integer and integer. So let's say I have all the keys values like 5, 7, 10, 11, but and each of these values correspond to something. Okay, and I want to get the value corresponding to 7 or 5 or something. Now there is no definite uh, arrangement as such. So in C++, like in having in C++ in general, I'm saying about data structures like map or any uh, data structure inside the standard namespace itself. And one can think of, like, in general, standard template library in STL itself, any class will have an iterator. It's a very convenient way of traversing all the data inside a class. You can even use iterators to traverse uh, vectors, arrays, and everything. The only difference is that the iterator sort of behaves the same way as um, uh, what do you call it? The pointers. Yeah. So, okay, I hope so far so clear. But the main idea is that when you have complicated types, as in like it will here the map begin itself has to be of type standard map with. You have to give the templates also whatever it was defined with, and then give the iterator. It's a uh, here the data type is not too large, but in cases there are multiple cases where you'll have data types to be too long, and it just makes it unreadable. So to have a clean code, auto is very useful in these cases where you can just avoid writing the whole thing and even make mistakes with the template parameters or anything, and let the compiler deduce the type of map begin. So because map begin, map underscore the object itself has been initialized with some types, okay, with the template types. So it knows which type to which exact iterator on in what namespace and all, like in what function itself it has to put it. Okay, so that's a very useful case, usefulness of this auto keyword itself. Okay, uh, yeah, a little further on the begin and iterators. So begin starts with iterator, and we have also end. End is the iterator to know where it ends. Where your iterator has to end. Okay. So similar to what we have in pointers. So we give sizes, right, to limit to which till which size we want to read the parse the list or something. Now you can have different examples like X has X's data type is known, so you can have like auto y equal to X, and you can even have const references, a const uh, data types, const pointers, const references. Now, important thing to note here is that auto itself just takes like let's say is inferring some data here. So it will take only the inbuilt data types like integer, float, and so on. It does not um, say anything about the constness of the data type. If we want a variable like say y here to be of const, okay, we have to make sure that it is defined, like we have to make sure that it is defined by ourselves. Okay. Now the three cases we saw are like you can have const variable itself, like const auto y. So that's one case with const auto pointer y, and you can just pass the address of x to have a pointer y. Or you can have like a const auto reference y equals to the map itself. So here the map underscore has a certain type, and y will infer that data type and then have like store a const reference to it. Okay. The same thing you can even do it this way, where C begin itself is a const iterator. Okay. The main difference is that iterator itself can change the data it is accessing. Const iterators can't. That's the main thing. So here the auto will have this data type, but the in both these cases, the functionality is basically the same. The difference is that y is const iterator. Auto here is const iterator by as in this data type. Okay. Then we saw decal type where uh, it's similar to auto, where it tries to reduce data types and such, but with a slight difference. We'll see that. So decal type. So let's say I take just define two integers. So as in not two integers, like first is the integer and second is a pointer. Actually, it is a pointer. So a and pointer b. So now what we can do is instead of writing some type and b, if I want to define it as data type whatever a is, so decal type is quite useful in that case. You can just type decal, like have decal type a, and then it infers the data type of a, so it will be integer, and then take that type and define b. So b is integer here. Similarly, decal type of p, and let's say I define q. So P is an integer pointer. Then Q is Q when it's defined is also integer pointer. You cannot do the same with auto because auto will not take pointers or references or constants. It doesn't like it doesn't infer those kind of qualifiers. Okay. Uh, that's one useful thing about that's actually the main useful thing about decal type. Okay. Then if we see some more examples, then so you can have let's say some variable defined as a equal to 9. Then I have a reference b to a, okay, which is the integer reference. Then I define another const integer c, storing it like having value 10. Then a const reference integer reference to c called d. What then I do is just have auto underscore a, like this variable is, I'm saying I'll define its data type auto by just taking a. Okay. So we saw that it will take integer. Then auto b, just storing b. So this does not store, like even if the data type of b is integer outside, as in it is a reference, integer reference, the data type of b, auto b underscore b is just integer. Okay. Then auto underscore c, while it is const integer c having value 10, the data type of auto underscore c is just integer. Similarly with auto underscore d. So auto itself, like we saw before, but I hope this example makes it a bit more clear. So auto itself does not have, itself does not uh, store any data type, as in these const qualifiers or the pointers and such. It can only infer the inbuilt data type, which is the integer, which is shared by all these variables. Okay. Then if I define auto reference, that is okay to make it reference to a. Here will be integer reference because it already detects it to be integer. We can have a reference by ourselves. Okay. So that is allowed. Then if I want it to be const reference, I can just add the const keyword. So it will be const integer reference here. If you want to have the sorry, exact data type as A, B, C, D here, we can just use decal type, where it reduces the type of A, and we are like doing sort of similar exercise as here, but with decal types. We can see the data type induced. Here it will be integer. Here it will be integer ampersand as in a reference because B itself is a integer reference. Then C, which is const integer, so you get const integer, and D as const integer reference, so a const integer reference. Okay. Another is the like useful function in a way you can say, which is the type ID, where it tries to detect the type of the variable that you're using. It's mostly useful in dynamic types where the type can change, as in it's a very specific use case has, but nonetheless, you can still use it to know the type of any variable. Another useful data structure we saw was the initializer list, where you can initialize a list of integers or variables or some data type, and then store some values to it. Okay. So there are three ways you can initialize some data. So one is using the equal to operator. Okay, so you store a as one. Another is the class way, in a way, like creating an object and initializing. So like a construct of a class, you can think that way. So here b itself, b is an object, stores one. And you can think like the class itself here is the integer itself. It is a class. But essentially the idea is that both of them are more or less equal. I mean, essentially equivalent. So instead of just writing a equal to 1 where you're storing 1 to a, here you have a object in a way of class integer and then storing 1. Essentially, you can think like b itself is integer and then storing 1. The third way is C, and just notice the bracket actually. So here it's just parenthesis, here it's curly braces. So the curly braces makes it initialize a list. Okay, it's just a collection of data you want to store and how do you want to parse. Essentially the idea. Okay, and let's move to okay. I hope my screen is visible. So right, today we'll be learning about lambda expressions. Okay, so these are very useful. How to put it? Um, Concepts in a way. Yeah, if I want to put it that way, they're quite useful actually in especially in C++. So um, the idea is that you sometimes don't want to write a full-blown function and then maybe write some lightweight functions and just on the fly call them. Okay, so that's the essentially the idea why lambdas are mostly used. So you do not have to um, like have full named functions and then uh, define it and then call it. You can just have that. So let's say some kind of function which you want to just use once or something. Hi, you can't see the screen. Uh, can people confirm? Can they see the screen?
Yes, sir.
Okay, great. Maybe it's just the internet. Please check again. Yeah. Okay, so where was yes. So the function itself, you know, let's say you want to just use it once, like define something and then use it once or on the fly, like or something.
Sir,
Yeah. Hello.
sir, it is showing terminal means Visual Studio, but not a code.
Yeah, I'm going to write. I'm just explaining the stuff. Yes.
Okay, okay.
Yeah. That's just the idea about what lambdas are. Yeah. Other thing is that you have, if you ever, so this is C++. So if you ever write code in SYCL, so it is SYCL. So it's majorly backed by, I mean, like the development now, I think Linux Foundation has taken it, but Intel is a quite a big contributor to it. So the idea with SYCL is that it's a sort of a universal language. So you just write, think of it like writing code in just C++, and it will run on all kinds of hardware. So be it CPUs, GPUs, FPGAs, or any other embedded device or anything. The idea is that you just write a code once, okay, and then port that to any other architecture. Because then now the thing is, it's just a slight uh, detour, but just bear with me. So the thing is, if you're trying to write codes for let's say GPUs or something, you have to be very architecture specific. You have to write in HIP, the AMD language, or if you're using like NVIDIA, then it has to be CUDA. Okay, you can write HIP also, so that I mean for AMD GPUs you can't use CUDA, so you have to write in HIP, which will work in both AMD and NVIDIA GPUs, but that doesn't run on Intel GPUs. So you have to write them in SQL. I mean, because of all this, Intel had this idea that they'll have this one universal language for everything. But what I'm trying to get at is the essential idea behind using like writing all this code once, like for all architectures. The main idea is that it just uses lambda expressions. If you see any SQL code, most of it is just lambda expressions. Okay, so this is a quite a useful concept, and then people just uh, quite routinely used, like in at least in modern C++ ways. Okay, so let's start now with some examples. Okay, yeah. So what I've seen before is I'll just give some examples first. I mean the SQL and all, you really don't have to worry about it, but it's something to keep in mind. Okay, so we'll have some kind of return time. That's fine. Yeah. So let's say I have some mm, how to put it, uh, some value. So let's say integer a equals to 10. Then I can actually write some kind of function. Okay. Um, so let's say not here actually. So maybe I'll just write it outside. So integer, let's say, yeah, we want to use the yeah, modulo operation. So let's say integer remainder. So it will take, let's say, some kind of value and and just return. Um, okay, I have to percentage by 8. Okay. Then closes. Okay. Now thing is, it will have access to A here. Okay, and this function will then take some value and then return the modular division. Okay, whatever remainder comes out to be. Now let's say I call this function by giving something with 10, right? So let's say 15. Okay, integer, and it should print 15, right? So there's a return. So I will maybe store it in integer remainder equals to 15, and then print this. Right? So let's see and compile this program. Okay, good. So G++, this time I'll just have with this, not this lambda, and probably function defined inside doesn't take it. Okay. Hmm. Name is the same. That's uh, okay. You can probably change the scope and all, which should work, but that's okay. Maybe just make it this way. Okay. So what I did here is have a variable, like essentially it's for just scoping. So I have a global scope A as 10, and remainder function, the function itself has access to this variable. 10 has 10. Okay. Now the idea is that the remainder function takes some m. Okay, like here it's 15, and then returns the remainder. That's what we're trying to print, which is it's printing 5 also. This is one way of writing a function where it accesses some pre defined values, okay, and takes its own parameters and then works with whatever predefined value, like whatever access it has, and then some parameter it takes. Okay, this is essentially what we want to do with uh, lambda functions. Okay, so this is a sort of a function, just a I would say motivation for lambda functions. Related is one. Yeah, that's the hashing fluid. And now the other way we can like make a function, okay, similar to what we did here, is make it a struct, make actually a struct. Struct are sort of, you can think of it like a very similar concept like to classes, what you understand in C++, but structs are defined in C itself. So then what to do is just have, let's say, integer none. Then the same thing is like a constructor for this class. Okay, so just integer then it takes, let's say, some input n and the value m stores n. Okay, no constructor required. Then as in it's a no body for the constructor required. This is the constructor. Then I'll just define operator, but this time I want to use the bracket operator. So I'm using the keyword operator. Okay, with notice the bracket here. I'm saying the parenthesis. Okay, with an input. Let's say m. It's why not? Um, maybe to the config. So let's call it an m. Yeah. So this will have a body. Shall have a return type. Okay, as the n, whatever the input is, divided by then percentage what we are dividing with. So there will be m. So it has an internally what it wants to divide with. Take value which it will divide by. Okay, so here in our case similar to that. So I had 15 and internally it will know it will have the value 10. Instead of having it outside in some scope, it will take that value and store it in its like a private member sort of. You can think that way, and then we use that value to return uh, the remainders, right? Slight difference, but the essential idea is the same. So you have some value outside, it has access to, as in what to divide with, and with each call of the function, it prints different remainders according to whatever inputs you're giving. Okay, similar to that only, we'll have a struct. So we do like struct, call it maybe run the remainder function. Then give it maybe, let's say, again the same value. Let's just give the same value 15. Oh, my bad. It has to it's the constructor, so I'll give 10. Okay. So then the rem itself is the function now. So we'll give pass it 15. Okay. And this. Now let's try to print this and then compile and print. Stay, oh yes. Oh, oh my bad. I missed this. This is the object goes on the right place. Yeah, so essentially the syntax also very similar to class itself. Only thing is that we don't write class itself, as in it's not required. So you write the struct and the struct that you are actually defining is remainder and then the ref. Yeah, let's print this also. Why not? This is the return type. Okay, so maybe we'll store this. There's no need to store. We can just print it on the fly. Then the line. Okay, see? Oh, great. So similar to the output as we saw before, the value a here. Maybe I'll just write it as anything else. What I'm dividing. N. Maybe make this as n. The second write as capital N. Okay. So n is the parameter that we want to divide with, similar to here what you are passing. Okay, in this function, and the value that we want to divide with. Okay, the function has access here. Here it's just a member variable here. So okay, maybe I'll explain this code once more. So okay. So what we did was defined a struct. Here we defined a function called remainder. Here we're defining a structure, okay, called remainder. The um, equivalent thing here would be to call remainder, okay, as the function. But here it will be the object that you call, okay, to pass some value or variable. Here I'm specifically passing a variable value 15, but there's a slight difference. But the idea is that here we had a function, and here we have a structure, a struct. So there it has an internal variable m, which it will store, which to divide with. Okay, so far so good. Then the constructor has it will take some parameters. So integer n, so some value n. So when I call rem like struct remainder rem 10, okay. So what it does is it uh, tells that I am creating an object rem, okay, of remainder struct, okay, and initializing it with value 10. So that's what the n here is. Takes the value 10 and then sets it to m, which is the internal variable. And then another operator that we have, which is like member of this object for like the objects of remainder can access, which rem can also access, is the operator. Here I'm defining an operator bracket. Okay, so these brackets are all defined now. So I can actually write this line. So rem the object, okay, with the bracket 15. Don't get confused. This is the constructor part. So next time, anytime you call, you'll actually call this function actually. Okay. So the operator here is defined to take some integer capital N, is that will be 15 here, and then just return n percentage n. Okay, m is already defined, and n capital N is what it takes. So it just returns that, and then we are printing it. Okay. I hope this is clear. Okay.
Yes, sir.
Okay. Great. Then yeah. So that was one way, the normal functions. Then we saw something called a struct, which are like actually functors itself. So maybe you can define functors now. It's essentially like how you um, define a function and then use it. So this struct was like actually in a way example of a functor. Oh, my bad. What next we'll do is define a functor. Okay, so let's say class functor. Think of it like mm, something close to a function, but it is actually a class. Okay. Um, but it essentially behaves like a function, as in how does it behave like a function? Because I'll have something with a bracket, call it, so it returns or does something. Okay. Uh, so here my rem object behaved like a functor, like a function. It's actually a class. I mean, as in a struct itself, but you can think structs as a class. I'm going to give the example of explicitly with a class, but the idea is that this is also a functor where you are um, like you have some kind of function which takes some input and then returns something, or doesn't return, or does something with it. So class functor. Let's see the example code actually. So that should uh, uh, make some examples clear. So integer operator. Wait, I will do it this way. Then have some integer, have some body. So it should return plus, let's say, like, okay, that is fine. This ends here. Now, what I can do is define this functor, which is like a function. So I have to use the type and then call it func, let's say. And I don't need any constructor, like what do you call it? The default constructor will take care of default constructor will take care of it. Um, so the func uh, object itself will be just using the default constructor. I don't need to pass any parameters to it. Then yeah, this defines the func, and let's use the functor that we defined to uh, print some values. So the idea will be very similar to what we used before. So here I had passed 15, but I can maybe then yeah, let's not worry about how to get access, like passing some value. We can write a constructor for it and pass that value here. Very similar to something we did here. So have an internal variable which will store the value it will be dividing with, and then so on. Okay. But let's just pass something and print that. Okay. I'll just say functor print. Okay. This should take care of it. Define a func, and the operator, like what we defined as the bracket operator, should take 5 and then just print it. Yeah, okay, great. Okay, good. So what we essentially did was defined a functor, okay, called func. Essentially, the idea is that it is an object of class functor, like what you're saying, but this is the concept of functor itself in C++, where the whatever the object you're defining, if you can see a func here, acts as a function. So the function will take value, and you're using this parent, like the parenthesis, the bracket operators, okay, and it returns a value. Here it returns a value. You can have not return anything like
Sir,
values. Yeah, go ahead.
sir, but what's the difference between the functor and function? Because it's look like it's just a class and you have used as a function, right?
Correct. The difference is that in work, as in the output wise, there's no difference. I mean, you can have plus here, you can define it as a normal function and then do it. The reason to do functor is it so we can have like a class like object behave as a function. It has its uses, but for this simple cases, you might think that I might just write a simple function. Yes, you can. I mean, feel free to. But the idea is that object can also behave like a function. Okay, by like syntactically at least. That's the Hence it's called a functor. That's it. It's just a concept. That's what I'm teaching. Yeah.
But what's the
Mm.
application then when we
Yeah.
go for functor?
Yeah. It application wise, think of it like you can have functions, sure, but I can't show you some with some simple examples. But sometimes when you have like huge codes where you want the some of the objects behaving like functions, uh, those cases you actually use it. Um, where you might think that why can't I just call some function? You can, you definitely can, but because of overloading and then it actually knows what uh, class it belongs to, right? Because this is an object of that class. It has other members associated with it. Whereas a simple function will have just itself, its data type, its inputs. That's it. But
Can I have means just sorry to interrupt
yeah,
you.
yeah, no issues.
Yeah, in that functor, can
Mm.
I have another function which will means a member function which will
Yeah,
be or member method which will be called to the means do something other means it has some different definition and it will do
yeah,
something
you
other
can.
thing.
Absolutely. Yeah. That is
But
the
then
useful.
how it will be recognized that it's a when to go for functor and when to I mean that object behave like a functor
Uh,
and when it will be go
the-
that object behave
uh,
like
so
another
let's say I have something called integer sum, integer n, and define and return. Sorry, n plus one. So to call this sum function, I will have to do something like this: func dot sum, and then pass an array. So
okay.
a general function, you'll still call it as a normally how you call from an object. So use dot or something.
Mhm.
Only thing is that now function itself, the func object itself behaves like a functor if you overload the, not overload, you define the bracket operator this way. And
Okay, okay,
yeah,
got it.
and this one is this way. Yeah, that's the
Just we can use only bracket operator or anything else also we can use.
you can use it anything, but functions, when you see something like this, right, then you think that, oh, this is a function with this bracket, because functions are defined with only the small brackets, the parentheses. Okay, these are for parentheses, right? Well, small brackets, yeah. Those, then it looks like a function. So hence I'm just sticking to using this operator, and then here the func itself looks like a function now. Okay.
Can we initialize with
If
initializer list?
yes, yeah, I haven't. You can. I haven't actually can have a constructor also. I haven't passed anything for the being for it being a constructor. But you can. You can make an initializer list also. Yes, and you can pass that initializer list to this function. Here it's
Mm.
just sorry here it just has integer n as like a single value. You can have initializer list and pass that initializer list also. Yes, absolutely.
Then we don't need a bracket operator, right? In that case,
If you define it
as
this way,
to
then if you define it this way, then yes, you need. As in, if you define it this way, you have to use the brackets. I haven't had a constructor here also. So as you see here, there is no constructor. The constructor, the uh, variables are not there. You can define it, pass the initializer list here itself or here. That's up to you. Yeah, you can do it.
actually what I mean to say that does functor has I mean it needs a bracket operator or it's not necessary to have a bracket operator on.
Uh, as in, when I say functor, I want it to behave like a function, so hence the bracket operator. That's all. That's what I'm saying.
Okay,
You can have other objects overloaded. So you can actually overload like this, let's say, my bad, like this actually, and then you have to use this operator. Okay, but this does not look like a function to me. I mean, generally
oh
because
yes, yes.
yeah, yeah, you can use this operator also, and then this is valid, as in it's not like it is wrong or anything. It's how you define, so it is using it. But uh, big bracket operator is generally used to access values. It's like a dereference operator. So the syntactically it is correct because it is valid, but code-wise it doesn't make much of a sense because people, once one sees this kind of operator, they will think we are accessing the value of a function of the function at 5. Right? It's not a pass. It's not a passing by value or passing by reference or whatever. Okay. Hence.
Okay, got it.
Yeah. Okay.
But bracket operator we are using for lambda, right? Lambda functions.
Yeah, I'm getting that. So that is that's the idea. So we'll use bracket operators there. The same idea is essentially the evolution. We have some function. Then in C, if you want to do the same, like the same thing, we'll use functors. So here it is also, the rem is also a functor, but written in a C style way where you're using structs. In C++, where you have classes, you write it this way. The idea is the same. It's like it looks very much like a class itself. I mean, structs are classes, so not much difference between these two. But the idea is that I'm using a class instead of structs, we have classes to make it as a function functor. I'm make a functor. Similarly, we can have now the actual thing that will be lambdas. So yeah, okay. I'll maybe write a just to keep in mind. Uh, Lambda have this sort of a any lambda expression. Okay, it has this structure. Okay, so first is the capture list. Then, like you mentioned, the bracket, the small brackets, which again takes the parameters or the parameter list itself. Okay, then the actual body of the function. Oh, 1 second. Yeah. So this will be body. Now there is a return type also, which it's not always compulsory to mention because the compiler can deduce it. But nonetheless, this is the whole structure of the lambda expression. Now, let's look at some examples. So you've seen this before. So let's go to the hello world itself. Okay. Now this is fine. As in, if I let's say run this program, good. It prints hello world. We've seen this before. The same thing. Actually, you can do one thing is what you can do is put it inside a function. Okay. More specifically, lambda expression. Okay. Where what I'll do is just have this. So the first starting with the capital brackets, the big brackets, and then the small braces says that this is a lambda expression with the body inside the the curly braces. Okay, and okay, I think it will end this program. No, okay. The good thing is that because of the syntax, compiler knows that this is a lambda expression. Okay. Now, thing is the capture list and the parameter list, you need not actually define it. I mean, they can be empty. It's okay. You can even have a empty body also. Then the lambda expression doesn't do anything, which is fine. But here we want the code that we saw just before to have some kind of body. Okay, so this one actually prints. I mean, let's just run it and then see the output. Okay, why did not after expression? Is it? Mhm.
That
Oh, yeah.
semicolon at line number 9.
Yeah, no, it's just a warning actually. That's fine. I mean, we haven't actually called this lambda expression, so hence no what do you call it? Nothing is generated. It's just a warning. It's not a compilation error actually.
Yeah, got me. Yeah.
Yeah. Anyway, so we define this, and to actually call this, we have to do this way. Yeah. So this should call it like a function now. Yeah. So that was the lambda function. Okay, this part. This whole
But
thing.
how many times I can call this? Means does I
You
can
can do
call
it
this
anytime.
after?
You can call it any number of times. So the idea is that we define this and store it in some kind of value, or like some kind of expression, let's say. We can have like I'll put it as auto and print equals to this, okay, and on it has this, and then call print this. This should work. Yeah. See? So then this print function functor, you can call it any number of times. Okay.
Yeah, got it, sir.
Yeah. So the idea is that the lambda expression, I mean, just let's just focus on the lambda expression itself. So it has a capture list, which is the big brackets, okay. Then the small brackets, which is the parameter list, has a body with a return type. Okay. Now this part is missing in this expression. I mean, the syntactically there is the big brackets and the small brackets are there, but we haven't defined any return type. So now the thing is, if nothing is mentioned usually, and if there is a body with a return or something, the compiler reduces the type. Okay. Here it will be void because there is no, it's just a print. There is no return or anything. So I just put auto here. It's like, again, just using auto to make that whatever print will do, like whatever inside the function is there. I don't need to worry what is the type of it. Will be void, but I don't need to worry. That's the thing. Now, putting this function into some kind of print, as this now the print here becomes a functor. You can use print and just call bracket because it doesn't take any inputs. So don't need to pass anything. And then if you call it any number of times, it just prints hello world. Okay. Great. Any questions so far? I think this part should be clear. Yeah. Then let's take more examples. Uh, okay. Then yeah. Again, hashing. Right. What I can do is uh, here what I did was have the lambda expression inside some variable like a name. I gave it a name and then reused it. Um, you can actually not name it and then keep it like so what we did before also. So uh, have it this way and just give it a so this last operator like having this I think you can relate. So having print and then we adding this small bracelet is what I'm doing here. Then it prints this hello world and maybe have it like hello world one, and these are all just hello worlds. So This should work. Okay, so it prints the old one once, and then the rest of them is just from the print function. Okay, so you need to still like lambda expressions to call them or to use the lambda expression, the functor. You still need to use this operator. Okay, that's just the way since functions are defined. So to use the functors which look like a function, also we use the same syntax. Okay, that's the only thing here. Okay. So, but what it did was here to use this functor, I did not, I did not give any name, but here I gave it a name and then used it multiple times. In expressions, in other examples, you can actually need not give it anything and still use it. I mean, that's up to you. So what I'm going to do is have a if-else statement. Okay. And inside the if condition, I'll have a lambda expression. Okay. So let's say it takes integer a comma b. Then now return type also right now I'm not I'll expect it to reduce. So mind you here it's taking integers and it's a if condition. So the return type actually should be a boolean. Otherwise for an if statement doesn't make any sense. So I'll return something like a equal to b. Okay, so of course it has to end. So if a is b, then it returns true. Okay, else it will be false. Now since the pg, yeah, okay. Now to use this lambda expression, okay, remember the syntax of lambda expression here. Oh yes, first with the big brackets, then you have the small brackets. If the return type is defined, then you have the arrow, else not required, and then there is a body with the curlies. After the curly bracket, whatever, if you give the small braces again, then the function itself gets called. Okay, so here my lambda expression expects two inputs. Okay, so integer a and b. So what I'll do is this is the bracket which calls the function. Okay, I'll give it 12, not 12, maybe let's put it 8. 8. So 8 comma 8. Now that takes care of the if part. Mind you, so the brackets for if are these. This is the bracket starting for lambda expression, then the capture. Then this bracket tells which will be the parameters it takes. So a and b integers. Then there will be a return, and then there will be the body. I don't have any return type. That's okay. So that's fine. I have a part of the body where I'm saying this will be the expression that will get evaluated, or this my function will do or return or whatever. So this is the body. I'm returning if a equal to b, as in if it is true, then this line, if it's true, it will return 1 or 0. Okay. Now to call this function, this is the bracket where I'm passing both 8 and 8. Okay, that's fine. Now it will take this as the input for the lambda expression. Compare 8 equal to 8, which should return true, like as in 2 or 1, to if. Then the body of if now gets executed. So we can write something like this. True. Let's call it true statement or something. Else false statement. So we know which part of the code it actually went to. Now here the thing is I could have had a function or a functor here and then pass the value. I mean, I can define it like we just did here with like print, auto print, and then call pass print with some values inside it. You can do that, or you can have a nameless function here. Lambda expressions allow you to do both actually. Let's print this. Okay, true statement. Great. Because the values are what I'm passing are same, so hence it's goes to the true part of the statement. I can do it this way also. Um, call it like a clause. I'll just use auto because again, it will be bull. We know that, but I really don't need to worry about it. Just put this whole thing, okay, and have clause. Okay, but this time I'll just use the part called clause with, now it behaves like a functor with taking values. Okay. Essentially, it's the same thing, but looking a little different. You can do both of them. Either is fine. Yeah.
Sir,
Yeah.
sir, it's a functor or lambda expression?
Uh, so that's the thing. Here it's a lambda expression. Okay.
Mhm.
I defined a functor using the lambda expression. So clause is a functor actually.
Okay,
But
okay.
but instead of this one, which is actually a function, this is the uh,
But
another
sorry,
mhm,
sorry to interrupt you.
uh-huh,
But functor is a class which has an object and that object behave like a function.
correct.
Am
That
I
is
correct?
slightly different, as in it's need. That's what I'm saying. A functor need not be a class itself. So we are saying that something which behaves like a function is more of a better definition. So
Oh,
here, the remainder or whatever, this one behaves, it is a function and it behaves like a function. That is one case. And the second case we saw is a struct which behaves like a functor, but drawn from a struct. Then here, a functor drawn from a class. Here it's a functor drawn from a lambda expression. It's like you want to have the same um, behavior, but you can achieve the same thing by three different ways. That's essentially what I'm trying to say. Lambda expressions are just another way of uh, doing what do you call it? The same functors itself. It's just another way of defining them. That's what lambda expressions enable you. Good. So first is true. It's what we saw with a nameless function. The other advantage of lambda expressions is you need not name them. So you can just I defined this function once and just used it once here. But since I wanted to later reuse it, I can define it like with a functor, okay, and then just call that functor. That's it. In that sense, they are quite, I mean, they're related in a way. You can think that. Uh, Calling this as a functor is also, I mean, it's up to you. We can call it as a not a functor. I can just say that this is a um, this one. This is the only thing that I'll call as a functor, which has classes. But the behavior that a functor has, like having some object or something which behaves like a function, can also be achieved by lambda expressions. Now, the nice thing is with lambda expression is that they are quite, you can just define it on the fly and then just use it. You don't need to have a full-blown function. That's all what I'm saying. Yeah. Of course, functors themselves are different if they're, I mean, let's think about objects of classes. So they have access to member variables and much further uh, use cases. So like even member functions that we saw here. Yeah, here. So you can actually define summit. Actually, we never compiled this. Maybe I should try this actually works. Okay, good. So this one, and then maybe you can print. So functor, you can just call it um, uh, this one here. Okay, good. So it prints the plus one with sum, and that's it. And maybe call it increment. Good. Yeah. So a functor, as we saw here, if it's defined from a class, then has different uh, other features that come with the class object itself. So yeah, but essentially what I'm trying to say is having something which looks like a function can be derived from all these cases. So either it's a full blown function, or it's a struct object, or it's a class object, or it's a lambda expression. That's it. Yeah. Okay. Now let's take another example of lambda expression. That's the as usual main. What I'll do is something very similar to this, but I was not able to have this function inside. As in, I mean, that's not allowed. But then I had to have it outside, have a global scope. Uh, then the remainder will have access to this m and all. Lambda expressions, um, what I put, give you the same features, but inside some function, like let's say main or something here, and it makes it easy to not have in scopes. So let's say let me show what I mean. So here I had defined integer n. So maybe let's just have the same code here. I'll define some integer n. That's okay. But then what I'll do is instead of integer, I'll now the remainder will be um, lambda expression. Okay. So the remainder equals to I should have the capture list. So capture will be m here. Okay. Sorry. Yeah, m here, which is this guy. It takes input as integer n. Okay. Notice the changes that I'm doing from going from here, like a normal function, making it a lambda expression. The parameters are same. Okay. The integer capital N and this braces. The extra thing is this capital braces small m, which is the capture. Okay. Then I have the body, which is exactly the same. The body of the function also doesn't change because it has exactly the same thing that I wanted to actually do. Okay. And then I have to end it. That's the slight difference because it's a functor like defining, so the end segment needs to be there. Then what I can do is then what I can do is just call this functor now. What I passed there was 15. Yeah. I hope the compiler reduces the type. Sorry. If it doesn't, then we'll give the data type explicitly. Oh, good. It did. So let's, oh, yeah, I forgot to print this. My bad. Sorry. Uh, Here I stored it. I mean, I could have actually done this also. Maybe that will be better. Okay. So let's print this and then see. Yeah, fine, great. So the same output that we get from one also is the same what we get here. Yeah, good. The slight difference is that instead of having a full-blown function, but then having a scope for it and all, uh, with lambda expressions, I can just have the same inside a scope of some function inside and just tell it to capture whatever variables I want. Okay. Now, the default behavior is that if you do not pass anything, it has access to all of them. That's the default behavior. I think the same with the parameters also. Well, I mean, as in parameters, it makes sense only to pass. If there is a capture, then you should not, I mean, if it has access to all of them as captures, it doesn't really make sense to have in parameters. But anyway, so then you have a return type, whatever you want to do. So what we're essentially doing is here is having a um, function which we are um, not explicitly defining, but just on the fly in a way, having a lightweight function that we uh, here we're defining it, sure, but we need not, and then just reuse it. It's essentially like saying, I want to have a functor, but without the class and all the other stuff that it comes with. I just want a simple one line inline function or something like that. So, yeah. So if we contrast it with this first function, first code, the same thing now written with lambda expression looks something like this. You can give it a data type or ask it to deduce using auto. Right. I guess we can take another example. Yeah, one thing to mention here is this uh, on this variable the variable m that is captured, okay, but it is captured by value, as in a copy is made inside. What I'm saying is, if inside this remainder lambda expression, where m is a uh, variable that I use, so with a return, so the small m itself uh, will not have, I mean, it captures the value 10, but changing this here will not actually change the value of m outside, as in the scope. I hope you understand. I hope you get the idea about scope here. So m has the scope only till this body or the lambda expression, because I passed m as a by value here. Okay. Uh, what I'll do is have another line. There's a return. So have like m as maybe 11. Okay. And then try to print the same thing. So, oh, sorry. Hmm. 6. Okay. Uh, okay, it's actually non-mutable, so we can't change it. Right. Okay. Anyway, that's fine. In the next by reference example, I'll just show you this. But okay, the idea is that the um, value that you're passing here, like even if it's a copy, you cannot change it. As in, that's even if you could change it, which we'll see in the next one, you cannot your the value that was there before. So let's say the n that will not have changed. Okay. So this remainder says 5 because integer is n. Okay, that's fine. The next way you can define the same thing is have lambda 7. Okay. All of them will just have the same code. Okay. The slight difference what that will do is have a reference. So previous case we had passed by in the lambda expression passed by value. Now we'll have a pass by reference. Then okay. So now let's say we can here what we can do is, since we are just returning something, we can probably add some other function. I think that'll be a better example to take. So let's say I have a running sum itself. So let's define it as 0. And this will be better actually. So let's not call it as an temp. Yeah. We call the function itself as sum. Takes temp as a reference. Okay. Take some integers and okay. Auto is fine. That's fine. And then here I don't need to return anything. I just want to store temp plus equal to n. Okay. So it will take the uh, temp as a reference, then have the value like the parameters itself will be n, right? Just 1 second. Yeah, sorry about that. So the value it takes its capital N, and then temp is the reference that we're passing. So I can actually modify it, as you saw here. Here it since it was a non-mutable copy, as in mutable, as in you can change it. Non-mutable means you cannot change it. So non-mutable copy here was created, but if you pass it by reference, so the same temp can now be changed. Okay, so the sum itself we can just have like sum temp. Actually, I should not because this doesn't have a return type. Yeah, you can call sum and then print temp. Yeah. So what we're doing is taking some value to that function, which is sum here, pass 15, the parameter, add it to temp, which is originally was, so 0, then it should, and then print the temp. Okay, let's see this one. Correct. It prints 15, and then later, let's say I repeat the same code again and again. Yeah, I can repeat the same code. And yeah, as you see, the value of temp increases. So the first time it is 15, then again 15 gets added because that's what we're passing, then 30. So the result is 30. After that, you add it again, so 45, then again 60. So passing by reference will actually have access to the temp value. So hence we are able to print it. Like, I mean, obviously here the scope of temp is inside main, so you can print it, but the value also gets changed. So for context of lambda expression, you can change values if you pass by references, okay, and mm, then modify them. Okay, so the capture has to be passed by reference. Okay, then let's see. Um, I think I gave the examples properly. So there's another thing about lambda expressions is called closure object. So think of it like classes and objects. So like we have a functor class and we made a func lambda expression as in the functor. So func is an object to this class. And when lambda expressions, so here I'm making is like a closure object. That's just a syntax thing. I mean, as in not syntax, it's a name thing. So sum is like a closure object here. So that's uh, you can think of like closures. So as objects are to classes, closures are to lambdas. That's it. We can maybe do some more examples. Yeah. Right. So let's take I just have a return statement too. Let's take example where okay. Another thing. So here we saw the captures and the inputs as the um syntax of lambda expressions. What you can see here is in this example, we had multiple parameters as input. You can have multiple captures also, multiple parameters input also. Okay. Okay. So let's take some example. And it can be mixed. So the capture themselves can be mixed. So for example, I'll have integer values equals to 0. I define this. Then integer reference because this val will be passed by a value. So it has to be defined, okay, and initialized as I'm doing it here. But references need not be initialized. So that's the necessary uh, syntax of lambda expressions. This is like lambda expressions have to have this. So the references need not be initialized, but values themselves need to be initialized. Okay. So I'll have like auto tick equals to, now here starts the lambda expression. This is the lambda expression that I'm writing. The value will get captured just by value, but the reference is my opposite. Yeah. The reference gets captured by reference. Now another is the parameter. I'll pass as parameter, just one parameter. I can have multiple param1, integer, param2, and so on. I'm just defining two for now. Okay. Then the body. Body is essentially okay. I'll just have principal. So it will look something like this. Right? So like have val as val, then ref as ref, then parameter one, parameter two, and ending. Now that it like this, define the thing. I have to end this. Okay, semicolon. Okay, now yeah, now what I can do is since I did not initialize ref, I can initialize it. Let's say 4. Okay, and then call the function check by passing. Now I have to pass parameters. So I can pass like 10, 11. Okay. I can okay. So let's do one thing. It will not have the ref, and then it actually should not. Yeah, it might have some throw some garbage. Let's good. So value was defined as 0, so that is good. Reference, as you see, I don't define anything, but that integer was, I guess some value was there, so it defined as 1. Parameters I passed as 10 and 11, so it printed those parameters. Okay, so here it's param1, param2, and so on. Let's see if printing it, okay, still has 1. That's fine. So let's say I define ref and then not do not pass anything to this check. That's the nice thing here. So because my check function captures something by reference, it takes something by a value. So it takes this val as a value, ref as a reference. I don't need to explicitly pass them here, which is fine. That's the nice thing about lambda expressions compared to in general functions, where in general function, unless it's in the global scope or something, it doesn't have any access to any other value parameter you pass it. Okay, unless it's in global scope, which is not usually recommended and not a good clean practice to do also. So having many variables in global scopes. Okay, but then in lambda expressions, I can just define val and ref inside some scope. Think of main as not just main, but some function, and the whole all of this will still hold good. So you can have val like defined with some value and ask your lambda expression to capture all this by value or by reference, and then change them or work on them accordingly. Now the ref itself I'm changing, and I don't need to worry about passing it to this check. Only I need to worry about whatever are the params that I'm passing. So since it takes param1 and param2 as two variables, I'll just pass values for those, and that's it. So let's see what is the print that we get. Great. So val is 0. Like no shocker. I mean, there's nothing uh, is as expected. The reference itself is 4. That's what we define. And as we can see, it reflects inside when we call the lambda expression. So the lambda expression now has ref as 4. Parameters anyway, we had whatever 10 and 11 before. So that's fine. Now what we'll do is, let's say, change value to 4. Oh no, let's call it 5 and call this function again. So any guesses what will happen with the output? Okay, we can print it and see. So it's exactly the same. The value of val did not change, even if I changed it here, because the that is strange. Uh, yeah, because when the function, the lambda expression is defined, it just takes the value copy. It just copies that value. But if you change reference, it takes it by reference. Okay, because reference ref variable itself is like a is taken as a reference. Wherever you change it and then call the function, it will have updated its value. Okay, uh, let's say I change it again. I'll call this value again. Oh, sorry, no, should actually properly change it. Yeah, yeah, as you say, it reflects as 70. Okay, nice. And parameters are as I mean, I hope you can see these are also passed by, like, as in these are just copies. So whatever you pass will just reflect it. There's nothing special about the parameters that you pass. It's more about the capture that is important. So the capture can be either by copy or by reference. References will reflect their values. Copies will be just once copied like once, and then always use the same value. Then you essentially, it's like you whatever it captures, you can change the value later and not affect your lambda expression. That's also a very nice thing about lambda expression if you can exploit it. Because these features or functionalities or um, uh, properties exist for lambda expression, you can exploit them to your code. I'll maybe make it one and so the parameters for the third call it as param1 and param2. Okay. Now, yeah, as we see, the reference was set as 4. So even if in the second call of check, we did not see the value of ref change. And when we change the ref again, like the second time here, then only the print of the check, the body of the check captured that new value and then printed it. Because capture is actually, if you think about it, when lambda expression is defined, it captures all these values. Okay, so val or ref or something. Ref itself was captured as a reference. So before the call, if the value itself changes in that place, reference all will because of the reference, it will know that. And the value itself will not affect anything because it has been captured. Okay. Okay, good. Any questions? I think this is clear. Oh, another example. We'll just see how the same thing if you write in C style structs. Okay, how will that look? But it's a cleaner way of doing things in lambda expressions. But you can do the same thing in using structs also. So let's see. Yeah, there's a question. Yes, that's the thing. So that's what I'm saying. So there's a question if the value is coming same when ref is changed to 17. Yes, that's correct. The reason for that is if you see the expression here, so I have this function main. Good. I define two variables, val and ref. The difference being that val itself I just initialized to 0, but I did not initialize ref. Okay, so far so good. But if you see the next line where check auto check is equal to done, here it's a lambda expression. And now for this lambda expression check, which is I'll call later, the capture happens by a value for val, which will be 0, and for reference, it is a the ref variable, it is a reference. So now if I change values for ref and call check, the value for ref, whatever it has access to, will change. That is fine. But for the lambda expression, as in this check itself, the capture was val, which is by copy, and it was initialized to 0. So later also, when you try to change, that um, change will not get reflected. Is exactly what we're seeing. So when I try to change ref first time, it shows 4. That's good because even val is also 0. I change it to 5. That's okay. Because for check, it had already captured 0. Okay. So even if you change it to 5 and call check, it won't capture as in it will just take these parameters and then run it as like a function. So think of lambda expressions capture part as when they are initialized, when they are first time called. That's when they capture all the variables, either by copy or a reference. Okay, then that part will not get touched. So this check, okay, will you can give different parameters. So accordingly, the values also change for parameters part. But for the capture part, if it's a capture by value, even if you change that, then there are two things to the capture by value. Okay, which is done while the initialization of the lambda expression happens, as in the declaration of lambda expression happens. So the value gets captured, okay, which is 0. So that is not going to change. And there's a reference. Now you have to be careful here for the this reference part, because if that gets changed anytime, so like here or here, the lambda expressions access will get changed. So the print itself gets changed here. Okay. I hope this expression is clear. Jan. Okay, great. Next, we can just see the example of, yeah, I mean, I understand this example can be a little confusing, but I hope the idea is clear, because with the lambda expressions, what you are in control of is the capture and then the body. I mean, there is a parameter and then the body. I mean, this has three parts. Body, I guess it's uh, straightforward that, yeah. So body, I guess, is straightforward. That's, yeah, sure. Yeah. Um, right. So the body is the whatever the function wants to do. That's fine. Parameters, as usual, like any generic function does. This extra part of capture, you just have to be a little careful with while dealing with lambda expressions. Your lambda expression first value, as in if it's it has some capture elements. So is it by capture by value or by reference? If it's a value, because it has to be initialized, that value will just get captured. So if you try to do it this way, it actually should throw error. Let's see, does it? Yeah. Okay. It captures the value that was initialized because it has some garbage, like some large number. It just captured that and then moved on. Maybe this will change if we do. Okay, it doesn't when we do it. Anyway, to keep it how do you put it? Uh, Clean and also correct. So let's stick to using predefined values. But again, as you can see, the behavior is that whatever value you are setting will just get set for the yeah, for the lifetime of that lambda expression. The reference, you can change it anytime, and then that value just changes. Okay, great. So let's see the other example with the same thing. Okay, integer var equals to 0. Then I have integer reference. I will not define this. Then I'll just write a struct. Now the same thing we'll just do what we did here with just structs. The um, what do you call it? The lambda expression way of doing things is clean, and this is a C++ script. If you do the same thing in C, how does that look? Again, as you can note, these are also functors. Okay, as in like the behavior is the same as functor, but with lambda expressions. Okay. I'll have this check f. Okay, integer value f integer with the struct part where will have private members. So the val will be the copy. Okay, so it will store that. The reference part comes now with a reference. So ref. Okay, then the constructor of the struct is essentially a class now. So you can have like integer value, integer reference, reference. Yeah. Okay. Then set them. Comma is comma required. Let's reference f as empty body. Yeah. So constructor doesn't need any body from in this case, so that's good. I need to have column. Then yeah, I'll have a operator, the void operator. Sorry. And yeah, I'll now, since we did two parameters, I'll have two parameters. Let's maybe copy this. Okay. Then add the body of it. So body, I'll maybe copy this. But now it has to have the access. So we'll print this one, then the reference, then param1, param2. Yeah, that's all. So now this struct is here. Now struct ends. That's all I guess. Yeah, the void operator also needs to end. Not, but let's see. Now, here is also another usefulness of auto. I don't need to worry about the data type of check that I'm defining. So the lambda expression was used to define the what do you call it? The functor here, like functor looking like a function check here. Here I'll use the struct to define the functor looking check. Okay. So this will be check. Checking values, I think val and face. So it has access to this rule. Let's do this. Okay, yeah, actually this should be, I mean, can put it outside also, but that's fine. So I define the struct, like the check from that struct, pass the constructor. Okay, so the struct is check underscore f, pass the values to the constructor, and on the values are set, parameters, then I can now pass the parameters to print this. So similarly, we can just do this one. Actually, we can just do this. Print this. Yeah, should work. Then great. Same output as previously. So value is defined to be 0. So when the struct gets this struct gets constructed, so the value was 0. So that's what gets passed, and reference get passed by reference. So when you call the first check with 10, 11 parameters, those are 10, 11. The parameters are printed. The value gets printed as 0 because that's what it was passed. The reference is set to 4, so that's what you get here. In the second print, before the second print, I change the value. Doesn't matter. the private member variable is already set. Exactly, in a way you can think like this is what happens in lambda expression also, as in the behavior wise. So changing it to 5 doesn't make any difference. It's still 0. The reference is 4. So that's what gets printed. And in the next reference and the next before the next print, the 17, when you change print 17 and I pass different parameters, so those get changed. Okay, so that's more or less it for lambda expressions, and the same thing you can do with structs. Let's see if we can have the thing outside and then print. It should be the same. Yeah, great. This also works. So yeah, it's like it's your choice. You can have it inside or outside. But yeah, it's essentially the same code, just re-implemented in using a struct. Uh, the nice with struct, because if you define it outside, it's like you have to have it predefined, uh, which is not required if you have it inside, which is like the same thing as lambda expressions. You can define it inside and reuse it. Let's okay then go with this way because this makes it closer to what lambda expressions are. But then the idea is that you don't have to write the whole constructor, private variable, and all that. Just have that all taken care of by the lambda expression. So that more or less covers lambda expressions. I hope you have understood the main idea. So important thing with lambda expression is you have to be careful with this yeah, syntax here. There's a capital list within the bigger brackets, the parameter list within the smaller brackets. So yeah, I did not put the data type, but those you can put something here, like here as an example. Sorry, as bool. So that is the return type here. So it will be integer. So it's automatically inferred from the by the compiler, but nonetheless you can explicitly put it or not. That's up to you. Okay. And the other part is the body. Body is, I think, straightforward. That's essentially what your function needs to do. So you just make a body. We saw example of a equal to b, so that should return boolean. Then we saw example of modulus, so that's the body part here. Then another with just a sum, so you're adding whatever parameter it gets to a referenced like the capture it did. Okay, and yeah, this one gives you a idea about the capture by value, the difference between the capture by value and the capture by reference. Parameters themselves are as usual. You can have it by reference or copy or whatever. But I hope the difference with the capture is clear here. Yeah, and the same implementation uh, of the code. You can have like through a struct also, so, and then use functors. Okay. Now I just think I think we'll all agree also. So it's just cleaner to use lambda expressions. Okay. All right. I think we can stop here with this. So if you have any questions, feel free to ask. We can end the class. Sure. Last program is this one. Okay. Yeah. Uh, if I just contrast, maybe I can just put it different. So I'll just put it as right. And that one here. Okay. I hope we can see the code side by side and then contrast the differences. Um, Till here, it's essentially the same. Only difference is that the check with the lambda expression and everything and the body of it, it's just done in a single line. Here you have to define a struct, have the necessary private variables. Like you have to write a constructor to define it, like have the initial variable initialized. Or you can also use default constructor here. But anyway, let's go with the user defined. User defined constructor. Overload the not overload. Define the operator, the small brackets. Take the inputs, then define the body and the struct. And then finally here itself, you have to define the check, which will act like a functor for us. So yeah, this is the check underscore f is the function that we are calling, and check is the, in a way you can think of like this is the object that is getting defined, and then we're calling all the rest of the stuff. So which are similar here. Okay. Yeah. Hope you guys liked the class today. Yeah. Thank you. Mm. Thank you. Thank you for attending.